Lusac's law. We've already compared pressure and volume and found that as one went up, the other went down. It was an inverse relationship. We compared volume and temperature and found a direct relationship. If I made something hotter, it took up more space. What kind of relationship do you think we have between pressure and temperature? Well, in all fairness, that's one that you guys are already well aware of. The pressure of a gas is directly proportional to the Kelvin temperature, assuming we hold the volume constant. So if I make something hotter, it will cause the container to have more pressure. And you guys all know this. There's a reason why we don't put a spray bottle of hairspray or spray paint on a hot surface like a stove or a fire. We'd be worried it would explode. So just like the variables of volume and temperature found in Charles's law, Gay-Lussac's law deals with a direct relationship. And for direct relationships, we divide. Mathematically, we are looking at P1 over T1 equals P2 over T2. Now, if heat's applied to the gas, the pressure inside the container will also increase. And the drop in temperature then causes the pressure to decrease. If I ask you again why this occurs, what I'm looking for you is to tell me what the particles are doing. Remember that heat is energy, and energy can't be destroyed. So if we give energy to particles, it causes them to move faster. They'll have more kinetic energy. And those particles will hit the walls of the container more often. Assuming the container can't expand and grow bigger, well, then the result has to be more pressure. More collisions equals more pressure. We have a couple of problems here that I'm going to solve with you. The first one has temperature and pressure. So again, what we should always start by doing is grabbing our highlighter and taking a look to see what the numbers are and what their units are. We have minus 33 degrees Celsius, 53.3 kilopascals, and 133.3 kilopascals. All right, let's go ahead and assign variables to these. Minus 33 degrees Celsius is temperature. I know degrees Celsius is temperature. Also, it tells us that in the readings. That helps us. So this is going to be my T1, there we go, of a sample of a confined gas exerts a pressure of 53.3 kilopascals. Now, kilopascals is a unit of pressure. And it's saying at this temperature, it has this pressure. So I can see these two variables belong together. And you actually do have to read the questions to figure this out. So I'm going to label that P for pressure, and I'm going to call it P1, because I can tell that it's at the same instance as T1. Now they're saying if the volume remains constant, what will the new temperature be? I'm looking for a new temperature when the pressure changes and reaches 133. This is a new pressure. Now remember, we've got three commonly used units for pressure. We have kilopascals, atmospheres, and millimeters of mercury. We really want to make sure that if I have two pressures in the same question, that we're using the same units. I have 53.3 here and 133 here. Both are in kilopascals. If one of them was kilopascals and another one was millimeters of mercury or atmospheres, we would have to change at least one of them so they were the same. And it doesn't matter which one you change, just so long as the units on the left are the same as the units on the right. Also, temperature, remember, for this unit has to be in kelvins. This is in Celsius. So again, I'm going to cross that right out so I don't accidentally use it. And I'm going to add 273 to it. And I will now have the temperature in 240 kelvins as my T1. All right. On your test for a mark, P1 over T1 equals P2 over T2. Again, show me the formula that you're going to use. It tells me that you understand what kind of question it is. And then we substitute. My first pressure was 53.3 kilopascals. My first temperature, 240 kelvins. My second temperature, 133 kilopascals. My second temperature, I don't know. That's what we're looking for. Again, when it comes to doing the math, start by drawing an x through your equal sign. Multiply the two numbers that are on the same diagonal, in this case 240 times 133, and divide by the remaining number. Divide that by 53.3. When we do this and we take the 204 kelvins and times it by 133.3 kilopascals, divide it by 53.3 kilopascals, what we see is that kilopascals here and here will cancel, and my answer will come out in kelvins. We end up with 599 kelvins. We should always ask, does this make sense? Well, my pressure increased by almost 3 times, so I would expect my temperature to increase by almost 3 times, and indeed it does. So this makes sense, and it is accurate. One more problem. Suppose a gas is in a rigid container and has a pressure of 33.5 kilopascals at 17 degrees Celsius. What will the pressure be if we cool this now to a temperature of minus 23 degrees Celsius? Again, look for the numbers. We have 33.5 kilopascals. We have 17 degrees Celsius, and we have minus 23 degrees Celsius. We should always start by taking a look at the wording and the units to try to figure out how to label them. This is a pressure of 33.5 kilopascals. I know kilopascals is a unit for pressure, and the wording tells us that. So I'm going to call this P1 for my first pressure. We have a temperature of 17 degrees Celsius. There's temperature. There's my T1. Okay, because they happen at the same temperature. There's my little linking word. And my T2 is quite a bit colder. Minus 23 degrees Celsius is going to be my new temperature, T2. Now remember, as soon as you see temperatures in Celsius, we can't leave them that way, so cross them right out, add 273 to them, cross them right out, add 273 to them, and immediately change them to kelvins. Once again, a formula is worth a mark, and then we substitute. P1 was 33.5 kilopascals, T1 290 kelvins. P2 is what we're looking for, and T2 is 250 Kelvin. Again, it doesn't matter what we're looking for, whether it's on the left or on the right, whether it's on the top or on the bottom. Find the diagonal with the 2 numbers in it. In this case, we're going to multiply 33.5 times 250 and divide by what's left. Divide by 290. In this case, we get 28.9. Because we had kilopascals as a unit for pressure here, we will get kilopascals as a unit for pressure there. The units on the left are always the same as the units on the right. Mathematically, this is going to be very similar to what we did in Charles's law. Now, in your textbook, on pages 447 and 448, they're going to talk to you a little bit about Gay-Lussac's law, and there's a few questions there for you to try. Hopefully, after this video, you understand the relationship between temperature and pressure, and you can explain to me how that happens in terms of how the particles are moving. And with some practice, I'm hoping that you can also calculate problems involving temperature and pressure using Gay-Lussac's law. I have a few questions for you to do on pages 19 and 20 of your workbook. As always, if you have any problems at all, please just message me through Teams, or if you're watching this on YouTube, make a comment below the video and I will try to answer your question. I can either work them out for you on a quick little how-to video, or I can email you directly.